So we are discussing separability in the last class. I missed only one thing, so which I will just complete. So there is something called second countability of a topological space. So if you have a topological space, if you have some X, a set, and we have a topological space, that means this is just a collection of open sets. You have X, this is just a collection of open sets. Okay. Space. Okay. Space set to be second countable. Before that, I have to say what is a base. Okay. Yeah, what's so I mean, if you have a topological space, then yes, generally this is defined for a topological space. Okay. So I mean, topological space is there is nothing. I mean, I have already defined. It is just you have a topology on this. We will study this in the next semester. So it is just a collection of open sets. You just declare it, and here it is just metric space. It is just open sets. Okay. Instead of defining through open ball, you define it generally. You define something which satisfies some axioms, properties.
Then need not be a metric defined.
There is no that. If it is like you just declare them to be open set. You just have a collection which is closed under, I mean, arbitrary union. Exactly, arbitrary union and finite intersection. Empty set, whole set is there. That is what is called a topological space. Then, I mean, and a B, you have a sub collection is said to be a base for this. Base for the topology tau. If every set here, every U in tau is union of that, U equal to union of some BI, I in I. Some collection, possibly arbitrary, uncountable, whatever. Okay? Arbitrary collection. Example, in a metric space, open set is, I mean, open balls. B equal to all open balls. Okay. This is the base. Every open set is a union of open balls, right? If you have any U contained in X in a metric space, then U equal to union of B, some any R, B epsilon X, okay, X in U, if you want. Any open set is union of open balls, okay. So if you have a sub collection of a topology such that any set in the topology is just a union of sets in this B, this is what is called a base, okay. And the definition is a topological space is said to be second countable if it admits a countable base. That's all. For example, in real line, you can take open intervals with rational endpoints, something like that. So, if it admits a countable base, that is, you have a sub collection of that such that everything can be written as union of that, which is a curve, which is a base. So now the proposition is, this is just useful. X is a metric space. Huh? No. It can be arbitrary union. This is what is, this says countable base. There is nothing countable about it. I mean, a set U, there is nothing countable about it. In a because in discrete metric space, again, there are also open balls are, I mean, open balls will be singleton. Finally, I mean, small open balls are singleton. So they need not be countable. B need not be countable. X is a metric space. Is second countable if and only if X is separable. It's actually very easy. It is just something, a remark basically. So, something is second countable. A metric space is second countable if and only if it is. So proof, if X is separable, let S contained in X be countable dense subset. Dense subset. Okay. Then Bx 1 by X in S, N in N is a base for open sets. I mean, when I say XD, it is all open, but the topology is just all open sets. Okay. So if you have, is it clear? I leave it as an exercise. If it is X is in S, that is dense. Okay, everything will intersect. So you can take union of such things to get any open set. Okay? I mean, any open set can be written as union of open balls, but then you can have sets from this which will cover that, and they are countable. This is countable because S is countable and N is countable. This is one thing. On the other hand, to prove this way, if X is second countable, that is B1, B2 is a base, okay? Then choose Xi in Bi, I equal to 1 to this, okay? That's all. S is equal to Xi. What is? Where is Y? Again, it looks like, now it's, okay. Now Xi, I equal to 1 to. This is dense, okay? That's all. I mean, this is just some remark basically. It's just the definition, and then there is really nothing involved in this. Now we will start talking about compactness. If it's all right. If I mean, if you have taken the notes or something. Okay, this is okay. Okay, exactly. Choose one Xi from that. That is countable. The Xi is countable. Something is separable means every intersection of open sets should contain something, but then everything will, I mean, have something, some BIs in that, and that will be there. Okay, just check it. It's very definition. It's just that from the definition it will follow.
First part. So B, like if you take the set with fixing one line, then it is also a B.
Say it again. Fixing
Fix one line.
1n.
You take, for example, you take B1X.
B1x. Yeah,
That
that
is also
if you have Bx epsilon, how will you get it? That is not contained in that, no? Bx epsilon. Bx1, you are saying you just take all those collection. What is Bx epsilon? How will you get it? Bx epsilon is an open set. So, I mean, Bx 1 by n, for example, you will not get it, right? So, yeah, you need all that. Okay. Okay. So, yesterday I stated something which I think all of you are, I mean, comfortable with the proof. That's something is total. I defined totally boundedness. Then I said that totally boundedness implies separability. I hope it's okay. Nobody wants it. You can work it out. Okay. Okay. So examples of totally bounded set. In Rn, all bounded sets are totally bounded. Okay. In Rn or Cn, of course. Rn or Cn, all bounded sets are I mean, I would prefer you to convince yourself. For example, if you are in R, real line, there is nothing. If you have a bounded set, then it is contained in a big closed open interval, something like minus RR. This, of course, you can cover it with any given epsilon, you can cover it with intervals of epsilon length or 2 epsilon length, whatever. And you just do the same for any bounded set, you can work it out. If you are in Rn, depending upon the metric, you can get it contained in a big open ball or something like this. Then you can have, I mean, see, something cross something. I mean, for example, I'm saying this kind of things will contain your open ball with, I mean, smaller epsilon. I mean, something smaller than epsilon, something. So you arguing that you can prove that any bounded set is actually totally bounded. Given epsilon, you will have finitely many open balls which will cover that. Okay, please convince yourself. Okay, so that is for Rn. But in infinite dimensional, bounded set need not be totally bounded. So that is where it, I mean, for non-linear space, it's only for infinite dimensional. In finite dimensional vector spaces, if you get a metric through a norm, then it is boundedness and totally boundedness are same. Only when the dimension is infinite, totally boundedness is something different from boundedness. Of course, totally bounded will imply bounded. Of course, you have finitely many open balls. You take a big open ball with some n epsilon or something that will contain everything. N epsilon, if you want to n epsilon, doesn't matter. Okay, you can have a big open ball which will contain everything. So totally bounded sets are bounded. Okay, but bounded sets need not be totally bounded. So that's what I want to show you in L1. So this is example. In L1, you can take L2, L infinity, everywhere this is true. In L1, define En equal to this sequence. Okay, this is a sequence, right? So 0, 0 up to 1, 0, 0, 0. Where at the nth point, okay, or En at k equal to delta nk. Okay, you are comfortable with this notation, no? Delta nk. When n equal to k, it is 1. N not equal to k, it is 0. So Enk equal to delta nk. This is a sequence. Wait. En bar equal to this Enk, where Enk equal to 1 if n equal to k, equal to 0 if n not equal to k. Okay, that is what it's usually called as delta nk. Delta means, okay. So this is a sequence, just 1 at the nth place, everywhere else 0. Okay, this is a sequence. And the distance between them, the L1 distance between En and Em, when n not equal to m, is going to be, I mean, it is going to be 2. No, 2. What? Delta n? 2. Number 2, right? It is going to differ in 2 places. Okay, I mean, it's going to be 1 somewhere, it will be 2. Okay, so if you take, okay, it's 2. So I will write it there. So if you take any collection of open balls, so in particular, I mean, the distance between them is fixed. Between En and Em, they all have norm 1. Okay, and so if you take bounded set, if you take B of 0, 1, okay, B of 0, 1, which contains, this is all those x bar in L1, such that norm x is less than or equal to 1, all these ENs are contained in that. En bar is contained in B01. Okay, this is just the open ball around 0 with radius 1. Okay, they all have norm 1, which is the distance between the 0 and En is 1. Okay, so this is contained in B01, all these En. So if you take any open ball, Bxi with say half, okay, with 1 is enough. Bxi1 and Bxi, I mean, if E1 is here, then E2 is, I mean, some En is here, Em is at a distance of 2. So both cannot be in the same thing. It will contain only one of them, right? If you take any open ball, Bx1 can contain at most one En. Okay, not more than that. It cannot contain two of them because the distance between them is two. Maybe half you take because distance can be two. So Bx half. I mean, it has to be. It doesn't matter. Okay, for safety, I'm taking X half. Now it's clear, right? So you cannot cover the whole thing with finitely many of them. There are infinitely many of them, right? Ens are countably infinitely many of them. So you cannot cover. So this implies B01 is not totally bounded. Okay, for the same reason, if you take L2, the distance between any En and Em, that is in L2 also, distance between them is going to be root 2, square root 2. And in L infinity, it's going to be 1. Okay, so there is a constant distance. When there is a constant distance, it's not possible. Okay, if you take open ball of half the, if you take given epsilon, you take half of that distance, okay, and you half over 1/4 of the distance. There doesn't exist finitely many of them which will cover that. That's the definition of totally boundedness. Okay, that's not possible. So this is not totally bounded. Okay. Okay. Now we define what is called compactness. Compactness it is some sort of generalization. I mean, basically, it's a generalization of finite set, or it is basically a finite interval. Okay, it is something, a generalization of that. So, I mean, this is a basic example. Basic infinite example is closed. I mean, any bounded closed interval, or you can take a finite set. Okay, it's something like a finite set. So, for example, in Rn, in any finite dimensional vector space, you can define closed and bounded sets as compact sets, and you can work with that. That's okay. But then in infinite dimensional, you need something more. It's bounded will not be enough. Okay, you need something called totally bounded. So you have to differ, and when you want to generalize to topological space and all that, you need the following definition, which looks bit. I mean, you must be knowing the definition, but which looks bit complicated. But we have to work with that. When you want to generalize the whole notion, we need something like that. So this is XD is a metric space. Is said to be compact, is compact if, so let's just write the statement and then write what it means. Every open cover admits a finite subcover. So what is the open cover? It is just a collection of open set which cover it. Cover means its union is that. Okay, open cover definition is clear to everyone. Okay, so it is just that is if U alpha from alpha in I, okay, is an open cover, meaning U alpha is open. That's all. You just have a collection open cover such that is equal to union of alpha in I U alpha. Okay, that's all. It is just you have a collection of open sets whose union is X. Okay, that is what the open cover is. Admits a finite subcover means then there exists alpha 1, alpha 2 up to alpha n such that X is equal to union of I equal to 1 to n U alpha I. That's all. You don't need all of them to cover it, only finitely many of them to cover. That's enough. Even if you have a finite set, for example, if you have a finite set, if you have finite set x1 up to xn, okay, then you can have, if you have an open cover, infinitely many, I mean, many things will repeat, of course, here. Okay, but then you only need finitely, each one is open. If you have a discrete topology, each one is open. You don't have finitely, I mean, you don't have infinitely many set. So you'll only need finitely many of them to do this, cover this. So the same thing is true for a, but this you need to, if you want to really go through this proof that this is compact, I mean, this has every open cover as a finite subcover. I would suggest you to go through some book. For example, Kumaresan is a very detailed it hasn't worked out in detail for that. But I mean, it will be messy here. Okay, I don't want to do that. But we will prove it through something else. Through sequentially compactness, we will prove it. We will prove it, but we will prove it through sequentially compactness. Okay, not every open cover has a finite subcover. Okay, but you can go through it. Okay, this is an example. But it is clear. But when you look at it, it is clear. If you have an open cover for this, okay, that has to something has to contain the endpoint. So you will get something. The endpoint will be. See, if you have open set, for example, then you can take this. I mean, you can take infinitely many of them. Okay, you can take 1 by, I mean, if it is 0, 1 by n, for example, okay, 0, 1, for example, okay, then you can take 1 by n, 1. Okay, this is an infinite cover which will not have a finite subcover. This is equal to un. Okay, then union of un is equal to 0, 1. But then it will not have a finite subcover. But when you include the point, some of it cannot be like this. You need to, one has to include the endpoint, and you will by arguing you can get a finite subcover. Okay. So this is the definition of our compactness. If you have any open cover, if you have any collection of open set which cover the cover X, then that is a finite subcover. Okay, that is one thing. And if you have a subset K contained in X is compact, if K contained in union of U alpha. So here it is just the containment, that's all. Okay, contained in that alpha ni. Then there exists alpha 1 up to alpha n such that K is contained in union of I equal to 1 to n U alpha. That's all. Okay. If you have a subset, then I mean this is not equal to, you just have it's a real cover. It covers it, and then yeah. I mean it has another meaning also. If you have a subset of any metric space, you can restrict that metric to this. Okay. Then every open set will be a open set in X intersection with K. Okay, you can prove it. This is an easy exercise. If you have a metric in X and you restrict it to a submetric, then every open set here will be some open set in X intersection K. Okay. Exactly. You know, you have to use open balls only. That is how it is defined. Yeah. It's a very easy exercise. Okay. So using that also you can define, or you can just take it as something covers this, and then it's a finite subcover. Okay. So this is compactness. The first proposition is, of course, this is easy. Compact implies totally bounded. Okay. I'm not writing in complete sentence. X is compact implies X is totally bounded. Okay. So the proof is easy. So you want to prove that X is compact implies X is totally bounded. So given epsilon greater than 0, okay, X is equal to union of B of X epsilon. X is in X, right? That is clear. Okay, everything contains X, so it is union of this. These are all open, and this is an open cover. Every open cover has a finite subcover. So compactness implies there exists x1 up to xn such that X is equal to union of I equal to 1 to n B xi epsilon. This is precisely the definition of totally boundedness, so it's true. Reverse direction, we will do it. I mean, we need one more condition and we will do it. Come here, we will do that. Okay. This is just this is a remark. Okay. This X is, how do you get open ball? You take a open ball. What do you mean by how do you get open ball? How this is true? Every X here is here. Everything here is contained. Everything, this is the universal. Everything is here. You have to prove everything is here. If X is here, that is here. Okay. So next definition is X is said to be sequentially compact. Is said to be sequentially compact if every sequence in X admits a subsequence, convergent subsequence, which has to converge there. Convergent means the limit has to be there. So if you have a fine, maybe for a, we can write the definition for a subset. Okay, maybe we write it for a subset. X is a, okay, then I mean in the whole set also it's true. Contained in X is said to be sequentially compact. Okay, if for all xn contained in K, there exists a subsequence x and K, a subsequence. I mean, this is okay. This is not notationally, it's not correct, but I mean, this is what I mean by subsequence. Okay, this is okay. K equal to 1 to infinity, that is n equal to 1 to infinity. Okay, subsequence such that x and K converges to x in K. It just says every sequence admits a convergent subsequence which limit in K. Okay. What is the? What do you want? I mean, I just said this means this is a subsequence of that. Okay. Not the right notation, but yeah, that's what I mean. Okay. Yeah. So every, it's just, I said it clearly. Okay. Every sequence admits a subsequence. Okay. Convergent subsequence. So example. Is it, or any closed and bounded set? Any closed and bounded set? Any closed and bounded set in Cn or Rn. Okay, let's consider C or R. If you have some sequence in C or R, I mean, you have seen the proof of this Bolzano's theorem. You have seen the proof of it, right? In the first course, yeah, Bolzano-Weierstrass theorem. So every bounded sequence has a convergent subsequence, okay, and it will be in the set if the set is closed. That's all. So if it is in R, you have a closed and bounded set. Okay, so then every sequence has a convergent subsequence. But in Cn or Rn, convergence is equal to coordinate convergence. So you take the first coordinate that admits a subsequence which is convergent. Now you take the second sequence, the subsequence of that admits, because it's finitely many stage, you will still get a subsequence because it's only finitely many of them. This will not work in infinitely many of them. So this is clear. This is an exercise. Okay. So if this is okay. If you have a closed and bounded set in Cn or Rn, then it's sequentially compact. If you have any sequence, you take the first, I mean, if some sequence converges, if and only if it converges coordinate wise. So you want to get a subsequence which is convergent. You take the first sequence, that is a closed bounded set in Rn as R. So you take a subsequence. For that subsequence, take a further subsequence. For that subsequence, go on doing it till for the, yeah, till reach the nth coordinate. Finally, you get a subsequence which converges for all of them, and because it converges in all the coordinates, the original sequence, subsequence, that corresponding subsequence will converge. Okay. If I have to write it, there is a lot of messy notation. So this is clear. Okay. So any closed bounded set is in Rn is sequentially compact. But on the other hand, infinite dimensional, this is again not true. This is non-example. Okay. Again, you take again in L1, x bar in L1 such that norm x bar 1 is less than or equal to 1. You can do the same thing in L2, L infinity, the same proof will work. Okay. Here you have En, okay, such that En minus Em, the distance between them is 2, right? Or it is root 2, or it is 1 in L infinity, root 2 in L2. Okay. And you have fixed distance between any two elements. It cannot have a subsequence. It converges because the distance between them should go to 0. It should be Cauchy, right? It should go to 0. So when there is a fixed distance between any two elements, that sequence cannot converge. Okay, because after some time it has to become less than epsilon, which will not happen. It will be always equal to 1. So it does not have it. So En does not admit the same proof, does not admit a convergence subsequence. Okay.
is to generate.
Discrete metric space. Yeah, there's infinitely many of them. Yeah, if you have any discrete metric space, the sequence converges if and only eventually constant. So that will not work. If you have any infinite sequence, it will not work. Okay. No, this is just a real example where this will not work. Okay, in infinite dimension, it's not true. Okay, you just take natural number with the discrete metric, that will not be sequentially compact, right? Okay. Okay. Huh? Yeah. En equal to 1 to infinity. This is a sequence. Okay. The En which we have already defined. Huh? Right. Yeah. It's no En bar or En whatever. It's just 1 at the nth place. Yeah, just here. Okay. Now next proposition. We have defined totally boundedness. We have defined sequentially compact. So first we prove X compact implies X is sequentially compact. First, let us prove this. Proof. So we have to prove X is compact. Then we want to prove X is sequentially compact. That is, every sequence has a convergent subsequent. We will prove the contrary, that if X is not sequentially compact, it's not compact. Okay. We assume the contrary, that it is not sequentially compact. That is, there X is a sequence which does not have any convergent subsequent. Then we prove that there is a open cover which is not which does not admit a finite subcover. So before that, this is a remark. X is compact. Okay, K contained X is closed. X is closed. Then K is also compact. Is it clear? So if K is equal to K contains in union of U alpha. Okay, then X is equal to union of U alpha, alpha in I or something, union that K complement, which is open. K is closed, K complement is open. Right? Now this will admit a finite subcover. Maybe this is infinite. This will admit a finite subcover. Take that finite subcover and remove K complement. Again, that will admit, because that is K complement. That is not, that doesn't have anything to do with K. So that will cover K. So you will get a finite subcover for this. Okay. So this proof is clear. I mean, you write the detail. Okay. So if K is closed, contained in a compact set, that's also compact. Okay. I use this here. So if XD is compact, then we want to prove XD is sequentially compact. Suppose XD is not sequentially compact, then we want to prove it's not compact. Okay. Suppose not sequentially compact. So suppose there exists a sequence Xn in X such that such that there does not exist any convergent subsequence. Okay. Then you take K just equal to union of, I mean, it is just the collection of Xn, but the point is Xn may repeat, right? So you just take it to be, if you want, it is just for notation. You just take all. It is just a collection of all Xn. You just take the sequence itself, but the sequence may repeat. Okay, it is just this. You take Xn itself. Xn, maybe it will repeat, doesn't matter. Okay. I assume this does not have any convergent subsequence. So the claim is K is closed. Huh? No Xn prime. Xn. There's no Xn. there doesn't, yeah, why is it closed? Closed means what? If you have a sequence in that set, if it converges, then the limit has to be there. Okay. So now you have a sequence. It does not have any convergent subsequence. Okay. But then you can form a sequence. So the claim is if something converges in this, okay, I mean, huh? No, it cannot have infinitely. I mean, if it has infinitely, say, suppose a a sequence from this set, K is a set. Okay, suppose some X, it will look like this, some Yn is contained in K, then Yn has to be some Xn K, right? Yk, then Yk has to be some Xn K, right? It has to look like that. It need not be, but Nk need not be like a subsequence. It may not increase. Things may repeat and all that, whatever. Okay, it may repeat. So if it contains an infinite element subset of this, that is not possible because that has to converge. That's up. I mean, if and Yk converges to some Y, okay, in K, Yk converges to some Y, okay. So it cannot have any infinitely many of them. It will have only finitely many of them repeating. And then it cannot have finitely many of them because after some time, I mean, it cannot, after some time it has to be eventually constant. If finitely many of them is repeating again, there is a distance between them. There is a distance, if you have finitely many of them, you take the minimum distance between all of them. That distance will be there between all of them. So it has to be eventually constant. Okay. Then Yk is eventually constant. Shall I go through the argument again? I'm saying you have a sequence in this. That means it has to be made up of this Xn. Okay. Suppose if it contains infinitely many Xn. I mean, suppose you have a Yk which is convergent. If it contains infinitely many of them, infinitely many Xn, then you have a subsequence which cannot converge. Okay, that is the number one argument. Shall I write all that? All the elements of K. Why should it have all the elements of K? Some of the elements. Yeah, a subset of A will have some of the elements of K. Why all the elements of K? Yk is a sequence in K. K is collection of these points. Yk is, huh?
K is the sequence itself.
K is the sequence itself. That's all. K is the sequence itself. The claim is K is closed. I don't know why this claim is K is closed. To prove something is closed, suppose you have Yk contained in K and Yk converges to some Y. You have to show Y is in K. Okay. Suppose, I mean, it just we have to write it in English, not mathematics. Suppose Yk, this sequence, contains infinitely many Xn's. Okay. That means it has a subsequence of this Xn. Okay. Then Xn, I mean, there is a subsequence of this, then there exists a subsequence of this which converges to Y. Okay. Then there exists a subsequence of Xn converge to Y. Okay. So which is not possible. So it cannot have infinitely many Xn's. It should have only finitely many Xn's. When you have finitely many Xn's, you take that finite set, you take the infimum of the distance between all of them, which is strictly positive. Okay. So if it is not eventually constant, that distance will be there between all of them, right? But it has to be, the distance between all of them has to go to 0 because it's a convergent sequence. Okay. So suppose I write that also. Okay. So this implies it cannot have infinitely many of them. This implies union of Yk is a finite subset. Okay. Okay, it's a finite subset. Okay, union of yk is a finite subset. I mean, even though it looks like this is a clear notation, very clearly written, all singleton yk, but it may repeat, okay, because it's just a finite subset. Okay, so now you take now x1 up to xi1 up to xin, okay, equal to this. These two are same. Okay, then you take delta to be minimum of the distance between them, d of x I k x I k prime. Okay, where k prime between 1 to n. Okay. I mean, that's why I said orally saying is more clear. I mean, clearer than this. Okay, I am saying that you take so this is made up of just finitely many of them, which may repeat. Okay, you take the minimum distance between all of them. That's all. That's what I'm saying. X I k prime, x I k prime, where you take the minimum distance between them. Okay, then if yk is not eventually constant, eventually constant means after some time it is not constant. Infinitely many of these things are there. That will mean that d of yk prime, okay, is greater than delta for infinitely many k and k prime, right? Okay, for infinitely many k and k prime. Okay, if it is not eventually constant. If it is not eventually constant, it has to change. Okay, so somewhere it will be some xi1 something will come. So infinitely many k and k prime, this will be greater than delta. So it cannot be Cauchy. So it's not convergent. Okay, this implies yk is not convergent. Okay, so this yk is in. So this implies from all these things we conclude that yk has to be eventually constant, and that will be in this set, of course. Okay. Yk eventually constant, okay, is eventually constant. Eventually constant means after some time it is constant. Okay, so this implies y is in k. Y is in that set, is one of those elements. Okay. So we have proved that k is closed. This implies k is so this implies k is closed, hence compact. Okay. We just proved k. We just proved. Why? We just showed k closed subsets are compact set is compact. Okay. So now the claim is there exists a delta n greater than 0 such that b of xn delta n intersection k is just singleton xi. Okay. I mean, I'm just saying for each xn there is a delta. That's what, because it depends on xn, I call it delta n. Okay, or fix a xn, then there is a delta such that this open ball around xn intersection k is just singleton xn. I mean, you have x1, xn like this, does not have any convergence subsequence. If such a delta n doesn't exist, okay, that means then each x1 by n intersection k will be something other than xn, but that subsequence will converge to this xn, right? If not, b xn 1 by k, okay, intersection k equal to some, I mean, contains some xk where xk is not equal to xn. Okay, this is okay. Xnk, maybe xnk, whatever, xk, fine, xk is not equal to xn. Then that xk xk will converge to this xn, which is a subsequence, which is a contradiction, which is not true. Exactly, that's what I said. If that exactly, that is what I'm saying. That is what this statement means. My intersection is xn. So if it is not exactly equal to this, if it's not the singleton, there will exist something else other than xn naught. So that means there will be a subsequence. For each k there exists xk. That xk will converge to this xn, where you fix an xn. Okay. So okay. So from all these things imply that this singleton xn contained in k is open. Okay, that's what it means by open. That is an open ball. The open ball around xn with the radius delta n is singleton xn. So that is open. A open ball is open, right? That is an open ball. Okay, this is open. Okay, now we are done. Now k equal to union of singleton xn. These xn's are open. Okay, does not admit a finite subcover. Of course, they are different, so you cannot have a finite subcover. So if we assume it's not sequentially compact, it is not compact. Okay? We assume there is a sequence with no subsequence, convergent subsequence. Then we took that sequence and we showed that each xk is open, okay, because it does not admit a finite, it does not admit a convergent subsequence. So then each of them is open, and from that, xk is whatever this xk is in this, that xk will converge to this xn. If this is not true, there will exist a xk, xk is not equal to xn. That's what this means. If this is not true. Yeah. Okay. Okay. Next proposition. If you are done with this, I will go to the next proposition. Okay. 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 So this is a property of sequentially compactness. Of course, we will prove sequentially compactness is same as compactness in metric spaces. So it's not true in general topological space. So this is true for compact spaces also. Okay. So X is sequentially compact, but for the time being, we are only using this property, sequentially compactness property. Then for any open cover, X is equal to union of alpha in I U alpha. Okay. There exists a delta. I mean, we are not assuming compactness. So finite there will be finite subcover once we prove sequential compactness is the same as compactness, but we are yet to prove it. Towards proving it, we are using this. Okay. So this says that if X is sequentially compact, then for any open cover, there exists a delta which will depend on this cover, delta greater than 0, such that for any X in X, okay, there exists a I in or alpha in I, such that Bx delta is contained in U alpha. What it means is the following. Just listen. If you have any X in X that is going to sit in one of the open cover, then you will have an open ball around that which will contained in U alpha, which is always true. There will exist a epsilon such that epsilon open ball is contained in that. But then the epsilon can be arbitrary. If you take the infimum over all epsilon, that will be 0. That could be 0. Okay, that possibly be 0. That is not the case. You will make a fixed delta such that a open ball of radius delta will be contained in that. Okay, you can fix this delta. Open cover, that's all. It depends on the open cover. It does not depend on anything else. Okay, for all X, you will get a uniform delta. For all X, there will exist some epsilon such that Bx epsilon is contained in U alpha. That epsilon can be, I mean, you can find an infimum of it. Okay, you can find a delta of it. That's all it means. Okay, that is what this is. This number delta is called Lebesgue number. Okay, this delta is called Lebesgue number of this cover. Okay. So this says that if it is sequentially compact, every open cover admits a Lebesgue number. So proof. Okay, we are assuming it's sequentially compact. Okay, we want to get a delta. U alpha contains R. No. Yeah. There exists an alpha. What does mean by U alpha contains Rx? For each X, there exists an U alpha. For different X, there may be different alpha. Okay. I was wondering whether I wrote it. Exactly. It is just that for each, that's what I said. For each X, there will exist an epsilon. But you can find a bound for that, lower bound for that epsilon. Exactly. Okay, that doesn't become 0. Yeah, that could be 0. It's just not the case when it is sequentially compact. And it is compact also. Okay, so we want to prove this. We are assuming sequentially compact. So suppose that does not exist a delta. Exists a delta greater than 0 with that property, whatever that property. Suppose there does not exist delta. That means for each 1 by n, I mean 1 by n is less than delta, each 1 by n, there will exist some element such that that is not satisfied, right? That property is not satisfied. Suppose then for each n in n, for each 1 by n, okay, there exists a xn in x such that b of xn 1 by n is not completely contained in U alpha. So intersection U alpha complement is not equal to empty. Is that right? Yeah. Okay. It's not completely contained in that, means it intersects with the complement. Okay. Intersect with the complement is not equal to empty. Yeah, for all alpha. Yeah. Maybe if it is not contained in some of them, it will be completely outside that. Okay. For all alpha. I mean, whatever there exists, we change it to for all alpha, follow. Okay. Just meaningfully we have to do. That's all. Okay. Now we have got an xn. We get a convergence subsequence. Okay. So xn as a convergence subsequence. Maybe you take the subsequence itself and assume that the sequence xn itself converges. Okay. Without loss of generality. Maybe you replace xn by another thing. So without loss of generality, assume. I mean, it has a subsequence, but if you want, you replace it by a different sequence and consider xn converges to x. Okay. Okay. Without loss of generality, you assume xn converges to x. Okay. Now we want to get a contradiction. What is a contradiction? The contradiction is we have already used sequentially compactness. We have negated this property. So this is what only we can contradict. Okay, the open cover has to be contradicted, right? What won't happen? What increasing? Xn goes to, because it's sequentially compact. Since it is sequentially compact, I am saying this. We are assuming it's sequentially compact. No, since X is sequentially compact, we are using that. We are assuming. We are as. As a subsequence converging to. Yeah, but I am taking that itself as the sequence xn. If you. Yeah. But that's okay. That doesn't matter. I replace xn with that sequence and work with that. Okay. Yeah. That is what without loss of generality means. we replace it with that and we don't. Okay. The thing is, we are assuming this is not true. We are assuming this. So, I mean, we are using this. So, we have to contradict this. I mean, we want to get a contradiction, right? We want to contradict this. Okay. So, the claim is X is not in union of V alpha. Okay. X is not in union of alpha. That is in intersection of V alpha complement. Same thing. Okay. V sorry, U is, I'm calling U. Why did I say V? Yeah, U alpha. The open set. U alpha. Okay. Written everywhere U and U. Yeah. We use U and V for open sets. Okay. Correct. Yes. Of course, everything is in capital X. There's nothing outside there. Claim. It's called claim. We have to prove it. Yeah. So the claim is X is in each U alpha complement. We have to prove that X is in the intersection of U alpha complement. So we have to prove X is in U alpha complement for each U alpha complement, right? Okay. So, I mean, I said it 3-4 times. What were you doing? I said that we take a subsequence without loss of generality. You asked it now. I said 3-4 times. I repeated that we take it without loss of generality. He asked. Everybody asked. I mean, you replace that sequence with this sequence. That's okay. That's all. Okay. You ask me to explain again, but when I have explained it very clearly, don't, I mean, better listen to that. Okay. That's all. You can ask me to repeat an argument. That's okay. And it's fun. It's nice. The class is live. Okay. If I ask you a question, it's nice. So it will be clear that you are listening. Okay. So what do you want? I want to prove that X is in U alpha complement for each alpha. That's what I want to prove. So suppose the contrary. Suppose X is not in U alpha for some alpha. Okay. For some alpha. Okay. You want to prove for all alpha. Suppose F is not in U alpha for some alpha. Okay. Then we want to get a contradiction. What is the contradiction? The convergent contradiction or whatever. Or we assumed that Bx xn 1 by n. This we assumed this. Okay. If X is in U, we contradict this. Okay. Okay. X is sorry. You are right. Sorry. Correct. You are right. Yeah, that's what we want to. That's what we want to. Suppose X is in U alpha. Correct. Yeah. Anyway, I would have corrected it soon. Okay. Yeah, this is the right statement. Okay. Then there exists epsilon because it's open. There exists epsilon greater than 0. Okay. Such that B of x epsilon is contained in U alpha. Just I'm using that it's open. Okay. All xn's will be there. When the distance between so after some time all xn's will be there, but with this epsilon the proof will not work, as you can see, because triangle inequality I want to use. So I choose since xn converges to x, choose n naught, okay, such that xn d x xn is less than epsilon by 2. I think epsilon by 2 is needed. Okay, epsilon by 2. Then if so, this is I have taken. This is an argument you should listen, so that I mean this. I want to conclude this. I want to claim something. The claim is b of x. We have xn 1 by n, right? That's what I want to do. Okay, I mean when 1 by n is less than epsilon, is contained in b of x epsilon if 1 by n is less than epsilon. Okay, that is the claim. To prove this, y here should be here. That's what we have to prove, right? So suppose y is here. That means suppose d x and y is less than 1 by n. Okay, then d y x is less than or equal to d of what is it? Y d yx is less than or equal to d x xn d x and y. Okay, and d x n x is less than I want to be less than epsilon, right? D x xn is, yeah, I have taken it to be less than epsilon by 2, right? Epsilon by 2 plus d dxy. This is also again epsilon by 2. This is also epsilon by 2. Okay, epsilon by 2 is equal to epsilon. Okay, that also epsilon by 2 if I take. Just look at it. Statement, if I have a y here, that means this is less than 1 by n. Okay, and I have taken 1 by n is less than epsilon by 2. Then use triangle dyx is less than this. This means b of xn 1 by n is contained in b of x epsilon, but we know which. Okay, but contradiction, it has to intersect with the complement. Okay, so b of xn 1 by n intersection u alpha complement, which is a contradiction to our assumption. Hence, hence what? Hence the x is a delta. Hence we are done. This is a contradiction, so such a delta exists. Okay, so we are done. Okay, UEB. Okay. This is what we wanted to prove.
Are we working with fixed cases?
Are we? Correct. No, I have used metric. What are you asking?
Like
Everywhere metric is used. Yeah.
Do we have to use metric spaces or can we work with Fibonacci?
No, sequentially it's not true. Sequentially compact. I mean, no, sequentially compact you can define. That is not same as compactness, or I mean, things will not work. What is that? I forgot. It's in Latin or something. It's not English. It's a, see, I learned it when I was in BSc. So after that, I forgot. So he remembers. It's fresh. Don't care. Huh? X? What is the claim? Yeah, X is not in U alpha. So X is in the complement of that. Okay, X is in the complement of that means, suppose that is not true, this is open, so there exists an open ball contained in that. Okay, so then since xn is there, then this is less than this. You can find after some time, choose n such that for all n greater than or equal to naught. Okay, then the claim is this is contained in this. This is the explanation of this claim. If we just using just triangle inequality, this is just the, suppose y is here, that means it satisfies this, then it satisfies this, which means it is here. Okay, which is precisely means it is there, and from that we can conclude that it is contained in U alpha, which is what we are assuming, which is not the case. You don't need to. Say it again. You don't need what? This. You don't need that means what? Claim is that, I mean, what do you mean by you don't need? Suppose that does not exist, this is not there. X and converges to X. Why? X is in all U alpha, not one single U alpha. I mean, X is in some U alpha, sorry. X is, claim is, X is, yeah, it doesn't cover is what I want to prove. X is supposed to be in one of the U alpha, which is not the case. Oh, okay. So, okay. So he has a point. I didn't really say what is actually contradiction. What we have done is the following. Okay, what we have done is this means, so X is, okay, you are right. X is not in union of U alpha, right? This means whatever, that's what we have proved. Alpha in I. That's what we have proved. That means X is not equal to union of alpha in I U alpha. We are assuming it's a cover, which is not the case. That is the contradiction. Okay. One more question. Correct. That is what I'm contradicting. Yeah. X is okay. You right. X is you some of the alpha. Which proof? Which proof? What will you do? X is in U alpha. What argument?
But that's the contradiction.
X is in U alpha, then X is okay. X is in U alpha. Oh, that's right. That's also fine. X is in U alpha. Yeah, that's what. Suppose X is in U alpha. I am saying X is not in. I mean, that okay. That's right. You are right. You are right. You are saying that X is in U alpha, so the same argument will work. Correct. Yeah, it is correct. Yeah, I'm just saying it's not a cover kind of thing. I mean, I'm just saying it's a, yeah, that's also a correct. Yeah. No, that's a better contradiction. Yeah, what he says is correct. Now, what he says is the following. Okay. I am just saying that X is in this. Okay. He says that X is in U alpha. Then you take this and then you show that this is not true. This is what we are assuming. Actually, that is where I stopped actually. But actually, in my argument, I'm actually contradicting this. Okay. This is okay. But you can, I mean, this is okay. Argument you are going through and you are contradicting this. What he says is, you don't need this. You take X. So X is, because it's a cover, X is going to be in some U alpha. Okay. Now you take the same thing. So there exists epsilon such that this happens. Then you use this, and that says that B of X and 1 by n intersection. I mean, that is completely contained in that. Okay? Which contradicts the original assumption. Yeah, which is right, which is better. Yeah. Anyway, it doesn't matter. Okay, so oh, we have taken so much time. Okay. So I have, okay, I will take some more time. I will finish this. Okay. I will finish at least some theorem or proposition, whatever. Okay. So the following are equivalent. Okay. You already proved many of it. So we will prove this. 1, X is compact. Okay. 2, X is totally bounded and complete. 3, X is sequentially compact. Okay. Okay. I will finish this. I will take some extra minutes and finish this. Okay. Okay. We have already proved X is compact implies it is totally bounded. Proof 1 implies 2. The proof of this. We have already proved if it is compact, it is totally bounded. We only have to prove it's complete. Okay. For that, suppose only need to prove X is complete. Assuming it is compact. So suppose if we have a Cauchy sequence, xn contained in X is Cauchy, we have already proved X is compact implies X is sequentially compact. Okay, implies sequentially compact. Okay, so there X is a subsequence. Okay, X and K converging to some X in X. Okay, now your Cauchy sequence as a convergent subsequence means the Cauchy sequence has to converge, which is triangle inequality. Okay, Xn Cauchy has convergent subsequence. Okay, you use you prove how to prove it, no? Triangle inequality. That's all. This implies Xn converges to X. Okay, so 1 implies 2 is fine. We are using the fact that we have already proved that X is compact implies X is sequentially compact and all that. Okay, so this is fine. Now 2 implies 3. We want to assume it is totally bounded and complete. We want to prove that it is sequentially compact. That's what we want to prove. Okay, so let us take some sequence Xn contained in X. We want to find a convergent subsequence of this. Okay, assuming it is totally bounded and complete. Okay, totally bounded means given any epsilon, you can find a cover. You can cover the whole space with finitely many open balls. Okay, I will not write each and everything mathematically in symbol wise, but I will make the statement, it will be clear. Okay, so X can be covered with finitely many open balls. So X equal to union of finite epsilon balls. Okay, some fall, you don't need to choose X1, X2, Xn. Okay, some balls. Okay, so there are finitely many balls and you have infinite sequence. So one of the ball has to constrain infinitely many xn's, right? So this implies there exists infinitely many xn in one of those balls. Okay, xn, infinitely many xn in a ball B1 with radius, let's say radius 1. Okay, I take epsilon equal to 1. Okay, with radius 1. I have a ball B1 with radius 1 which contains infinitely many. Now you close this ball, you take the closed ball. Okay, now the closed ball is contained in X which is compact. Now B1 closure you can take or B closed ball you can take. Okay, I mean both will work. Okay, so B1 contained in X is compact. Okay, now this is totally bounded. Subset of a compact is totally bounded. If it is compact, it is totally bounded. We have proved. So because of that, B1 can be covered with balls with radius half. Okay, so there exists B2 bar contained in B1 bar with, with radius half containing infinitely many xn. Okay, you have from X you got a ball which contains infinitely many of them with radius half. Now you have a radius 1. Now you have, that's a closed ball. Inside that B1, B2 is contained in B1 and you have a which has radius half which contains infinitely many balls, because this will be covered by balls of radius half. Okay, now this can be covered with balls of radius 1/4. One of them has to have something like that. So we have the following. I'll write there. So there exists so this is true. There exist balls Bn n equal to 1 to infinity, ball Bn closure. Okay, closed balls. There exist closed balls. Okay, Bn closure with n equal to 1 to infinity with radius 1/2 power n. Okay, containing infinitely many of them. Many xn. Okay, and the diameter is decreasing, right? D of Bn bar goes to 0. And it's a decreasing family and it is closed. So Cantor intersection theorem. Theorem implies intersection of Bn closure is singleton X for some X. Okay, we have proved it. Okay. Now you take any closed subset of a compact set is compact. X is compact. X is sorry, totally bounded and complete, right? Yeah. So okay. Yes, sorry. Fine. Sorry. It's not compact. It is. So I made a mistake. It is totally bounded. Subset of a totally bounded set is totally bounded. I'm sorry. Yeah, sorry. Someone should have corrected me. Yeah. In the flow, I said that. Yeah, it is just subset of a totally bounded set is totally bounded. That is clear, no? If you can cover the bigger one, you can cover the smaller one. Yeah. Sorry. Correct. No, I am just covering B1. Now B1 closure is totally bounded. I am covering B1 closure, which is totally bounded. I am covering with open balls of radius half. Then you have something inside that. Huh? I am covering B1 closure with which is totally bounded. B1 closure is contained in X. X is totally bounded. Subset is also totally bounded. Subset of a totally bounded set is totally bounded, right? Correct? So B1 closure is totally bounded. Now you cover B1 closure, which is totally bounded by radius open balls of radius half. Since B1 closure contain infinitely many, this is finitely many of them. One of them should contain infinitely many, right? Exactly. Yeah, infinitely many n such that infinitely many of the Xn is contained in that. That's what it means. Yeah, you are right. Infinitely many n such that this may it is true. Then you have a subsequence. It will repeat. Yeah, I have to. So that is why I said as a sequence infinitely many terms of the Xn's. Yeah, or what you said is correct. Infinitely many n for which Xn is contained in that. That is okay. That's what I mean. Okay. Now you choose one element from this, each one of them, Yn in Bn. Okay. Yn in Bn intersection Xn. Okay. Then this Yn will come. This will be a subsequence and Yn will converge to it. Okay. Okay, that's all. You have a subsequence, it's converged. Yeah.
I just have an alternate route for this, which I think is a little simpler. Maybe there's a problem with it, so I just want to run it by you. So you have got totally bounded. We have seen that infinitely many points of this sequence will lie inside one of the balls of radius epsilon. So since we can do this for every epsilon, we essentially have a Cauchy subsequence, right?
Which is subsequence of what?
Of our origin sequence X. Since all the for a given epsilon, since infinitely many points lie inside that epsilon,
so
use a prime inequality.
If you have something, then all you have a subsequence which is contained in B epsilon. Correct.
So we can show that X is itself Cauchy actually. So,
yeah, I think that is there a problem with that? If you have a sequence, you have an open ball. There are finitely many. One of them will contain infinitely many of them. That is a subsequence, and that subsequence is Cauchy.
yes.
That has to converge. Correct.
So you basically have a Cauchy subsequence, and
That's
since it's
correct.
complete, the converge.
That I think so.
Oh.
I don't see any problem with that. That's right. Anyway, this is also true. Okay. Yeah, I think so. Okay. So what have we proved? We have proved 1, 2 implies 3. So 3 implies 2, 3 implies 1, we have to prove. That's all, right? So 3 implies 1. Okay. So we have to prove it is compact. Okay. Something is sequentially compact, then we have to prove it's compact. Huh? Yeah, yeah. So sequentially compact, we have proved, we have assumed that there is a Lebesgue, I mean, there is a Lebesgue number for that. Okay. Yeah. So from that, we want to prove something. Wait a minute. Yeah. So since, okay, we are assuming X is sequentially compact. Okay. So there exists a delta greater than 0 such that for any X, and we want to find a subcover, something, right? Yeah, quite subcover. X is sequentially compact and assume X is equal to union of U alpha, alpha and I. Okay. These are open cover. We have to find a finite subcover. Okay. 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 Now there, since X is sequentially compact, there exists a delta greater than 0 such that for all X, for any given X, for any X in X, there exists alpha in I such that the X delta is contained in U alpha. Okay. Okay. Now we want to claim is, the claim is the following. There exists x1, x2 up to xn such that X is B of xi delta. Okay, this is the claim. I mean, the claim is there exists finitely many x1 up to xn such that this happens. That is the claim. We assume sequentially compact, so we got a delta which we have proved. Now we assume that this, I mean, we assume that there is so cover for that we have a delta. Now our claim is there exists finitely many such that this happens. Okay, if this is true, each B of xi delta is contained in this. So this is equal to union of alpha. I mean, if xi is, I mean, if B of xi delta is contained in U alpha I, okay, now this is also equal to union of I equal to 1 to n U alpha I. So we are done. Because Bxi alpha is contained in U alpha I, right? That's what we have assumed. So then it will follow that X is union of this also. Correct? So this is what we have to prove, right? If we have x1 up to xn such that this happen, then this is contained in this, okay, for some alpha, which I call it as alpha I. For xi, I call it as alpha I, then this is true. Okay, so this is what I have to prove. I have to prove finitely many of them is there. This is what I have to. This was done earlier, no? So I will erase here. Is fine? Okay. Suppose not. Suppose there does not exist finitely many. Okay. Then fix any y1 in x. Okay. Then of course x is not equal to b of y1 delta. I mean, certainly, because finitely many, so singleton cannot cover. So there exists a y2 such that d of y1 y2 is greater than delta. Okay, because this is not equal to this, there exists some y2 such that this is greater than this. We are contradicting. No, we are we are contract sequential compact. Correct. Yeah. Correct. Okay. Now x is not equal to b of y1 delta union b of y2 delta. Okay. Because there doesn't exist finitely many. That's what we are assuming. Okay. There exists y3 such that d of y1 y2 less than delta, sorry, greater than delta, d of y2, y1, y3 is also greater than delta. Okay. So going this way, there exists y1 a sequence such that d of yn, ym is greater than or equal to delta for all n not equal to m. So you cannot have a convergent subsequence. This implies yn does not have convergent subsequence. Okay. So that has to be true, that it is covered by finitely many of them. Okay. Now we have already, I mean, that's what we wanted to prove. We are done. Yeah, question? Okay.